session number 5. The keynote speaker, Professor Kamel El-Khatib. Professor Kamel El-Khatib, Professor of Chemical Engineering, Engineering and Land Department, Engineering Research Division, National Research Center. He has been working on developing the different kinds of new nanomaterials, electro-catalysts, and development metallic bio-polar plate for polymer electrode-membrane fuel cell application with water treatment and electricity generation using microbial fuel cell. He has experience in process design, technical evaluation for different industries, and techno-economic analysis. Also, he has an experience in water desalination using thermal and membrane technology. He published more than 80 peer-reviewed papers in international journals, 15 papers in conferences, and 6 papers in national journals.
Good afternoon, everybody. First of all, I would like to thank my dear Professor Dr. Ahmed Shaban, the former Vice President of National Research for Technical Affairs, and thanks for Dr. Heba and Dr. Marwa for their invitation to be attended the second International Conference for Membrane and Technology Application. My presentation would be different than the other presentation for water desalination and water treatment. My presentation will be in energy section, especially for fuel cell technology. My presentation title will be Development of Proton Exchange Membrane for Fuel Cell Applications. My presentation outline, I will give an overview about the fuel cell technology, what is fuel cell and how it works, history and types of fuel cell components, fuel cell efficiency, advantages and disadvantages, and the application of fuel cell. I will give also a case study about the membrane application in polymer electrolyte membrane fuel cell. There will be a case study to Dr. Hanaa will be presented, but unfortunately will not be available today. The idea of fuel cell technology is like the battery is electrochemical system which convert electrical energy to electricity. But the only difference of fuel cell technology is continuous production of electricity by using fuel and oxidants. As you know, the battery, or we have two types of battery, primary battery and secondary battery. The primary battery, we have to use it in running little devices like remote control and other devices. And we can use it for one time and dispose of. The second battery, we can recharge it and reuse it for more than 500 cycles. And we remove it after finishing their cycles. As I mentioned, the fuel cell technology is continuous production of electricity. This is the only difference between fuel cell and battery. And as we can see in the animation photo, animation picture, we have two electrodes, anode and cathode, and the electrolyte, which is the membrane. The commercial membrane used is the naphthalene membrane. And as we can see in the anode side, the hydrogen dissociates to two hydrogen protons and two electrons. The two electrons goes to the outer circuit to produce electricity, and the hydrogen protons goes through the membrane, react with the oxygen on the other side, and the electrons to produce electricity. The history of fuel cells started in 1839, discovered by Sir Williams, and he discovered the fuel cell. He firstly made the electrolysis of water to produce hydrogen and oxygen, and he found that when we connect the anode and cathode, it produces energy. There are 5 types of fuel cell, and it's named depending on the type of electrolyte used. The first type is proton exchange membrane fuel cell, and its operating temperature about 60 to 100 degrees centigrade. The second type of fuel cell is alkaline fuel cell, and the operating temperature between 90 and 100 degrees Celsius. The third type is phosphoric acid fuel cell, and their temperature is about 175 to 200 degrees Celsius. The fourth type is molten carbonate fuel cell, and its work about 650 degrees Celsius. The last one, which is solid oxide fuel cell, and its working temperature about 800 to 1000 degrees Celsius. The fuel cell components consists of end plate to assemble the fuel cell, and current collector, and the gas diffusion layer, and a proton exchange membrane, and 2 electrodes, anode and cathode. And we use platinum as the electrical catalyst for this application. If we look to this graph about the fuel cell efficiency compared to the other technology for electricity production, we can see that the fuel cell can reach to about 65% efficiency comparing to other technology like diesel electric and gasoline electric and steam and gas turbine. The fuel cell characterization, they have general advantages of fuel cell. They direct energy conversion, no combustion, no moving parts in the energy converter. White, there is no noise. Fuel flexibility, we can use hydrogen, methanol, ethanol, and carbon monoxide or carbon dioxide. Modular installation to match load, and we can manufacturing fuel cell stack can produce 1 watt, 10 watt, 100 watt, and 1 kilowatt, 10 kilowatt, and so on. Size flexibility, and we can make different stacks like series of stacks back to back. It is environmentally friendly. It is only produce electricity and the water, and there is no pollution that comes out from the fuel cell. The disadvantage of fuel cell is market entry cost high due to the materials used for the fuel cell using platinum as a catalyst, and the vacuum membrane is very costly, and its meter square cost about $600 to $1,000. The endurance and durability of higher temperature units is still under research, and the lifetime not exceed about 400 hours. The other disadvantage is no infrastructure for fuel cell application. The fuel cell application can be applied for electric vehicles. As you know, the electric vehicles running now using battery. The second generation will be using fuel cell for running electric cars. And can use it also for buses and small applications like mobile, laptop, and small fuel cell stack for running some appliances like TV. And also we can manufacture the fuel stack with 250 kilowatt for application in most of hospitals, restaurants, and some applications. The commercial used membrane for fuel cell is Nafion, and its a chemical composition, as you see, from polytetrafluoroethylene backbone with perfluorinated vinyl polyether side chains containing sulfonic acid group, which is responsible for proton exchange for the hydrogen. The proton exchange membrane, as we can see from this figure, represent about 45% of the total cost of fuel cell stack. So the most research running for replacing the naphthalene with lower cost. This is some of the physical characterization of different naphthalene based on the different thickness. And this is the physical properties of each membrane. Our case study today for manufacturing a protein exchange membrane to be applied in fuel cell instead of naphthalene. We make sulfonated hyperbranched polyester and sodium titanate nanocomposite as protein exchange membrane. ودي الخطوات اللي احنا هنتبعها في تحضير الممبرين. اول خطوه ان هي synthesis of hyperbranched polyester, synthesis of sulfonated hyperbranched ether sulfone polymer, preparation of titanium dioxide nanowires, formation of hyperbranched ether sulfone titanium dioxide nanowire nanocomposite membrane. The end of formed nanocomposite in sulfonated hyperbranched ether sulfone matrix. The first step of preparation, the synthesis of hyperbranched polyester by mixing hydroxide phenyl varylic acid with dimethyl amino pyridine toluene sulfonated and dimethyl formaldehyde. This mixture will be done under stirring in the presence of nitrogen gas for 30 minutes, followed by adding coupling agent dichlorohexyl carbodiamide. ده برضه في وجود النيتروجين جاز وستيرنج لمده 24 ساعه عند درجه حراره 25 درجه مئويه. The results will be white precipitate of hyperbranched polyester. The second step of preparation, synthesis of sulfonated polymer hyperbranched ether sulfone with sulfonic group. This is done by mixing the first step with dimethyl fluorine plus sodium hydride. This is under nitrogen gas and 25 degrees centigrade for 16 hours. And the mixture will be, we have to add butane sulfone as a source of the sulfonic group to the mixture. And this step running under stirring with 25 degrees for overnight. And then adding droplets of 10% hydrochloric acid and stirring for 25 degrees for 24 hours. And produced high-branched ether sulfone SO3H. We prepared two types of this membrane based on the sulfonation degree, 15% and 100% degree of sulfonation. The third steps would be synthesis of sodium titanate nanowires as a composite. We prepared by adding titanium dioxide to sodium hydroxide, running in autoclave at 240 degrees for 3 days. We produce white precipitate of nanowire, and followed by adding 1 mole sodium carbonate for 3 days under vigorous stirring. And this is a picture showing the same analysis for the titanium dioxide, sodium titanium dioxide nanowires. The third steps will be synthesis of hyperbranched ether sulfone with adding the sodium titanate to the polymer. This step done by mixing equimolar amount of high-branched ether sulfone and sodium titanate nanowires in tetrahydrofuran. This step running under sonication for 30 minutes with vigorous stirring for 3 days. Dried the nanopowder under vacuum at 50 degrees centigrade. Membrane preparation, we prepared two types of membrane, blank membrane and composite membrane. The steps of preparation blank membrane, we prepared two solutions. The first one, sulfonated hyperbranched polyester dissolved in dimethyl formamide and stirring overnight. Second, the solution would be polyether sulfone as a support material was dissolved in normal methyl pyridine. Then the two solutions were mixed and stirred overnight to form a homogeneous viscous solution. Then casting the solution onto a glass surface with a controlled thickness, about 100 micrometer, using a Dr. plate technique. Immersing the glass plate in a non-solvent bath water at room temperature, washing the membrane several times using distilled water to remove any traces of solvent. Then the membrane were dried by standing overnight at room temperature. This is the same analysis images for the prepared hyperbaric ether sulfone with sulfonic group, blank membrane. As we can see, there is no pores and the surface is smooth. The composite membrane prepared as the same method before, but the only step different is adding the sodium titanate to the composite. And this is also the same images of the composite membrane. This is the same images for the composite membrane of polyether sulfone with the titanium dioxide. As we can see that the sodium titanate is covered with the polyether sulfone. And this is another image for the membrane. And we have measured the mechanical properties and water uptake for the membrane for the 50% and 100%. And as we see from the graph here, that the naphthalene membrane is the highest mechanical strength, followed by the composite membrane with 1% of titanium dioxide in the composite. And we perform NMR spectra for the membrane before sulfonation and after sulfonation. And we can see from the second graph that the OH group is not found after we make the sulfonation process. That means the sulfonation process, the sulfonation group replaced to the membrane. We conduct the thermogrammetric analysis of the composite membrane. As we can see from the TGA for the naphthalene, is stable until about 400 degrees. There is no degradation. For our membrane, we lost about 13% of the 100% composite membrane. For the second membrane, 55%, we lost about 27%. But this is the temperature. We run the fuel cell at about 100 degrees. This is the picture of the membrane after casting, before adding the electrodes to the membrane. Figure A showing the membrane without adding the electrodes. Figure B, the membrane after adding the electrode to the membrane. We have testing the membrane in a fuel cell test fixture. This is a figure for the fuel cell test station. It has about 110 centimeter square fixture for running the performance of the fuel cell. And this is the performance of the fuel cell comparing to the naphthalene. As we can see, the naphthalene is the highest one, is about 60 milliwatt per centimeter squared. The second one was the blank membrane. And the additive of titanium dioxide, sodium titanium dioxide to the membrane, showing a less performance than the blank membrane. And this is another test for degree of sulfonation of the membrane at different immersing of membrane in sulfuric acid after 2 hours, 12 hours, and 48 hours. And 20 hours immersing showing the best performance for our membrane comparing to the naphthalene membrane. This is another We have manufacturing a stacked fuel cell producing about 100 milliwatt using enough membrane of our membrane, and we have running and it produces about 75 watt per centimeter square. And this is a picture for go-kart using a fuel cell stack for running the car. This is done by a cooperation between the National Research Center and US Egypt projects, and we perform it, and we have a good performance using a fuel cell stack. Thank you for all of you.
Thank you, Dr. Kamel. Any questions?
You tell us about some problems with uses of data. Your voice. Could you tell us about some problems you face in producing this prototype?
Some problems facing you when you preparing your product. Actually, we have facing different problems for manufacturing the byproduct or to have a goods and the byproduct. We tried several times in some industry to manufacture these byproducts, but unfortunately, we didn't find the right material for manufacturing and machining, using the same machine. For that, I have sent this to the design for somebody in China, and they make for me and send it to me. It's the only problem I did. Second problem may be the leakage during the filling of the stack, during the gasket, the thickness of the gasket, and thickness of the floor. So this makes some trouble for me during that. The second speaker will be Professor Frank Nussbaum, Professor of Fluorite Concentration and Technology in the University of Hanaa Science. From Germany, since Professor Census 2015 has been working as Professor of Fluorite Process Engineering at the University of Applied Science. His focus is on ceramic process technology, including membrane and wastewater technology for more than 20 years. Dr. Lunar has been involved in the development of energy and resource efficiency processes, especially in the food industry, chemical industry, and manufacturing industry. Dr. Lugar, you can start your presentation.
Hello, good afternoon. Can you hear me?
Yeah.
You can hear me. Okay. So at first, I would like to thank you for the invitation. So I'm very happy to present you some findings that were partially made in my lab together with some students. So Lena Tetampe is a member of the of my university. That's the University of Applied Sciences in Cologne, in Germany. And Lia Zagitova was an exchange student from the Polytechnical University of St. Petersburg in Russia. And together they were working on several aspects that will be shown here today. Well, what can you expect today? So at first, I will introduce shortly basic principles of electrochemistry and the electrodialysis, which is the main topic here. The second part will focus on the application in the metal industry. So the first example will show the concentration of lithium-containing solutions on lab scale. And the second example will focus on the treatment of stainless steel pickling solutions on industrial scale. So that means on a real life plant. Well, and then I will shortly summarize the findings and give some outlooks on electrodialysis as a technology for environmental technology. Well, at first, I would like to introduce electrodialysis. So it's an electrochemical separation process that works with ion exchange membranes. So we have installed between a cathode and an anode a multitude of so-called repeating units. So these repeating units consist of one cation exchange membrane, a diluate chamber, an anion exchange membrane, and a concentrate chamber. So when the current is applied, the ions move towards the respective electrodes. So that means the cations are moving towards the cathode and the anions are moving towards the anode. And this movement is to a certain extent hindered by the installed membranes. So the cation exchange membrane allows only the passage of the cations, and the anion exchange membrane allows only the passage of the anions. So that means the ions of the opposite charge cannot move through the respective membranes. And another effect that we will find and we will see afterwards is also that ions of the same charge but with a higher charge number are also hindered from passing through the respective membranes. Well, and as I said, this technology is based on a multitude of these repeating units mounted between the electrodes. Well, there's a lot of parameters that influence the performance of this electrodialysis process. So one thing is connected with the setup of the plant itself. So that is the current density. That means the applied current in relation to the respective electrode or membrane area. So then we also find some effects that come from the hydrate shell of the ions. So that means every ion carries with it a certain amount of water. And this is also what we will see afterwards. So that means that the movement of the different ions is also influenced by the size of the respective hydrate shell. So then we find influencing parameters concerning the flow conditions. Certainly also the membrane properties are important for the process, and also the respective properties of the diluate solution that we generate and the concentrate solution. And certainly also the material of the electrodes influence the whole process. And in any case, when we are talking about membranes, we are also talking about membrane fouling. So fouling is also an aspect that influences, at least over a longer time, the performance of such a electrodialysis apparatus. So, but here in this case, we will not see any kind of membrane fouling. Well, then we will also go into some electrochemical terms. So the electric charge is something that we will see afterwards. So the charge is in principle the integral of the applied current multiplied with the respective working time. So then we have the electrical current density. So that's the electrical current in relation to the respective membrane area. And as a performance parameter, we have the current efficiency. So this is the relation of the applied electrical charge in relation to the real transport of ions. So 100% current efficiency would mean that all of the applied current is used for the transport of the ions. But in all cases in real life, we have losses that may be caused by heating of the solution. It may be caused by side reactions at the electrodes. There may be also a decomposition of water, so-called water splitting, and this also consumes the current that we have applied, and so this leads to losses in the performance. Well, with this, I will come to the first example. So the concentration of lithium salts on lab scale. So lithium is a key material for the future energy change. So in the moment, the main sources that we have are minerals and clays. And the most important source for these for the lithium is brines, mainly coming from China and from the Andes in South America. So here we have, in principle, in all kinds of sources, we have rather small lithium concentrations. So, and in near future, hopefully we have another source, a secondary source, and this is spent lithium-ion batteries, or LIBs, which are recycled after use and can be used as a source for the new lithium winning. So the problem is, as I said, the very slow concentration of the respective lithium inside the sources. And another problem is that we have a lot of other disturbing components that we need to remove before we can concentrate and regain or gain the lithium. So for instance, aluminum, boron, manganese are some of the most important disturbing substances that need to be removed. And this means that in all winning processes, we have a multitude of different concentration and separation steps. So it's not only one step that is used for lithium winning, it's a multitude. And one of the possible steps that can be used in such a process is electrodialysis for the concentration of the lithium that is dissolved in water-based solution. So here you can see a test plant that was used. So it's a small test plant with different tanks that are used for the feed solution that becomes later on the diluted solution, then the concentrate solution. And we also need a third solution for this application. That's the electrode rinse that transfers the electric current from the electrodes into the water-based solutions. So this is a rough setup of the plant. And here you can see how we started. So at first we started with ideal solutions. That means we took lithium salts, dissolved them, and took the conductivity as a measure for the concentration of the respective lithium inside the respective dilute and concentrate solutions. So, and from these measurements, we could find an algorithm that combined conductivity with the respective concentration. So the experiments were operated or were done in a batch mode. So that means you fill the tanks for the dilute and the concentrate, then switch on the electric current and then wait what happens. And what happens is seen here. So the conductivity of the concentrate solution rises at first until it reaches a steady state. And the concentration of the dilute is decreasing also until it reaches a specific steady state. Well, and certainly this is not enough for a technical process. So if we want to increase the concentration of the concentrate much further, so then we would leave the concentrate solution inside the tank and use a new dilute solution from which the ions are transported into the concentrate. So and this is shown here on the next slide. On the left hand, you can see the conductivity over the time. And you see every time when we change the respective dilute chambers, the dilute solutions. So then this would be this point, then the concentration of the dilute is rising. And again, during the process, it is the conductivity is falling because of the transport of the ions into the concentrate. Yeah, and same is here to be seen when the change of the dilute takes place, then the concentration of the concentrate again starts to rise. So, and another way to describe this process is not to use the time, but the electric charge. And when we look at the electric charge as a function of the conductivity, then we can see that we come to a nearly linear slope, and this is according to Faraday's law. So this is what we can expect, that until a certain concentration of the lithium, we have a linear dependency of the conductivity and the charge. So then we tested several different lithium-containing salts, which are important for the production of the LIBs, so that's lithium chloride and lithium hydroxide. And we could see that they show different transport behavior, although the experimental conditions were kept stable, as we can see here. So this is the slope for the lithium chloride, and this is the slope of the lithium hydroxide. So this depends on the respective hydride shell that is fixed to the respective ions. So these were the results of the first example, and the second example touches the recovery of spent pickling solutions. So pickling of stainless steel is an important step for the generation of clean surfaces that are really stainless. But this process requires expensive and aggressive acids, and they are mixtures of nitric acid and fluoric acid. Well, and during the pickling process, the concentration of these acids gets down, and the concentration of dissolved metals inside this pickling solution rises. And then there's a certain point when the pickling velocity is not fast enough, and so the pickling solution should be exchanged. Certainly, this is not the best option to discard it in terms of economical and ecological interests. So therefore, we should face recovery of the still active components of these pickling solutions. And we can remove the metals and could recover them afterwards. So, and here we can see such a stack that was introduced in real life in a stainless steel producing company. So there was a multitude of these stacks. You can see that they require high voltage, and also the current is quite high. So this process is working or is requiring a lot of energy. Nevertheless, this process was required because the steel producing company was forced to reduce the emissions, especially of nitric and of nitrates, into the receiving waters. So what you can see here is again a setup that was comparable to the lab scale experiments. So here you can see the concentration rise of the concentrate. So here over the time, the concentration or respectively the conductivity was rising over the time because we kept the concentrate solution and exchanged the respective dilute solutions once a minimum conductivity was reached. So if we go into detail, here is the sketch of the free acid. That means the protons that were transported during this process. And we can see that there was also more or less a linear increase of the proton concentration in the concentrate. Here we can see that the efficiency was in the range of 45%. That means 45% of the electric energy that was supplied to the stack was transferred into the ionic transport. So then we can have a look on the nitrate concentration. Here the behavior is quite similar. So the nitrate concentration was rising linearly, more or less linearly with the time. And also here in this case, the current efficiency was in the range of 45%. So this was what we could expect. But when we look now at the fluoride concentration, so fluoride or the fluoric acid is a very expensive component. So it would have been nice to recover it as well in the concentrate. But what we can see is that the concentration of the fluoride keeps more or less stable here in the concentrate and also in the dilute. That means we have hardly any transport of fluoride ions, and this is attributed to the fact that HF is hardly dissociated and therefore cannot be transported in the electric field. So then we have a look on the metals. So this combines the concentration of iron, chromium, and nickel in the solution. And we can also see here that the metals are hardly transported through the membrane. So they remain in the initial solution. And this is what we wanted to achieve, to separate at least the nitric acid from the metal contents. So the formed dilute contains more or less all the metals, and this can be used for further metal winning. And the concentrate solution with a high concentration of protons and nitrates can be fed back into the pickling zone of the metal producing company. Well, another effect that I already touched in the beginning is the transport of water. I mentioned that the ions, they carry a specific hydrogel, and they when the ions are transported, so when nitrate is transported, it carries with it also several water molecules. And so this leads to an effect that the volume, so here this is the relative volume over the time, so the volume increases over the time because water is also transported into the concentrate chamber. So that means we have to consider when we design a plant that the volume will not keep constant, but will rise in the concentrate tanks. And the same is true for the dilute. So the dilute solution is losing the respective water molecules. Well, so with this, I come to a summary of these findings and of electrodialysis itself. So some effects limit the applicability of electrodialysis. So I didn't mention the costs. So in this case, we have to consider that certainly an energy consuming process can only be implemented technically when we have a reason for it. So at first we have to check if the costs are justified. So in the case of the pickling acid recovery, we can say that the steel company had only two options in this case. They had to reduce the nitrate concentration in their wastewater, and otherwise they would have been closed. So therefore, the costs didn't play a role. So the other alternative would have been to close down the factory. And a similar factory was installed in Sweden, and they also had the problem that their wastewater spoiled the receiving water, and also their authorities urged them to do something to remove nitrate from their wastewaters. So then, apart from this, we can say that we have some things to consider. So first is the limiting current density that leads to water splitting. So when the electric current is too high, several side reactions take place at the electrodes, so-called water splitting, and gas, that means hydrogen and oxygen, is generated in effect that is not desired because we want to transport ions. Next thing is the electric leakage during the through the frames of the modules, then back diffusion because we have a relative concentration between dilute and concentrate. Then we have other leakages through the membranes, so especially proton leakage of membranes is detected. As I said, sometimes also scaling and fouling appears, but this can be compensated by cleaning or by specific operation conditions. So accordingly, the total costs of such a plant is a factor of several parameters that are shown here. I won't go into detail. So there's a lot of things that you have to think about before you install such a plant. But nevertheless, we can say that the electrodialysis equipment market is reasonably high, with about $300 million US. And the growth until 2025 is expected to be 4% per year. So, and the most important segments where electrodialysis is installed is seawater desalination. So that's the dominating part of the market. But as I said, recycling and the environmental market become more and more interesting, because with the help of the electrodialysis, it is possible to separate ions from each other, and also including protons, and to recover on the one side, for instance, acidic solutions, and to increase the concentration of valuable metals in a waste solution or in a production process. So with this, I have come to an end. Do you have any questions?
Thank you, Professor Lugar. Any question? Yes, we have one question.
I would like to tell Professor that several authors in the literature consider electrodialysis and electrodialysis reversal as obsolete due to the low percentage.
Well, I can hardly understand you. I can't answer your question because I didn't get a single word. The connection is not so good.
Okay. Thank you, Doctor, for the interesting presentation. I would like to have your opinion about some authors in the literature defend that electrodialysis and electrodialysis reversal are obsolete due to low recovery and the cost of system and operation as compared to reverse osmosis. Thank you.
As far as I understood, your question was concerning the performance of electrodialysis compared to reverse osmosis. Well, this is always a question of the concentration of the respective solutions. So with reverse osmosis, you can achieve very small concentrations of salts. With electrodialysis, you normally always require a certain amount of ions inside the solution, or otherwise there will be no electrical transport. So therefore, the electrodialysis may be an important step for the total desalination. But in many cases, the setup as shown here cannot be used to achieve waters with a very high quality. That means with a very small ion content. But there's another setup that can be used. So you can fill the respective chambers of the electrodialysis with ion exchange beads. So this is so-called Electrode Ionization. So, and the Electrode Ionization can now compete with reverse osmosis. So there's a multitude of these plants installed, for instance, for the generation of water for power generation. So this is a standard in Germany, that pure water or ultra pure water in power plants is generated with this kind of electrodialysis filled with ion exchange. Yeah, but the setup that I have shown here cannot compete with reverse osmosis.
Any other question? Thank you, Professor Brown, for your nice presentation and your participation.
I have one remark, may I? Okay, so I was very happy to be with you, in fact, only virtually. So I would be happy to meet you next year and see you from face to face. And I would like to cooperate with you. And we now have a better possibility to cooperate, because yesterday you have seen Miriam Sator. With her, I have been working for a long time. And now again, she became my colleague. So we are now strong in the membrane field, in different applications of membranes. And I saw so many interesting approaches from you. So I would be very happy to cooperate with you in the near future. Thank you.
Yes, yes, Dr. It's our pleasure to meet you and cooperate with you. We have very interesting and impressive presentation. We all have interested with your talk, and hope to meet you soon in Egypt and cooperate with you soon. It's our pleasure. Thank you.
Thank you too.
The next speaker will be Dr. Mahmoud. Dr. Hadda from National Center, Hyperthermia and Water Pollution Research Department. The major research is about water treatment priority, bioenergy, multi-biomass, and bioactive environment production. She has only published 14 peer-reviewed journal articles.
Good afternoon to all. To continue the talk session, I will speak about bioelectrochemical framework dominating microbial flow cell performance, especially the technical bottlenecks and potential solutions. Simply, microbial flow cell is a bioelectrochemical system by which we can use different microbes, electroactive microbes like bacteria, fungi, and recently microalgae, for biodegradation of the organic substrate present in wastewater, and transfer the electrons produced through this process to the anode surface, and then these electrons move to the cathode through external circuit producing bioelectricity. Besides bioelectricity, The microbial fuel cell technology can be integrated with other technologies like biofuel production, like biohydrogen and bioethanol. Also, microbial fuel cell is considered as eco-friendly and cost-effective technology for desalination in comparison to thermal distillation and reverse osmosis. In terms of wastewater treatment, microbial fuel cell technology not only can degrade organic substrate, but also can be used for sensing and monitoring pollutants present in the wastewater, like dyes, heavy metals, or pharmaceutical wastes. Despite this advantage of the microbial fuel cell, it still faces technical challenges in terms of low power and current density, restricting them to powering only small-scale devices. And so the description of some of these challenges and their solution may be of great interest when the microbial fuel cell applied on a large or commercial scale. First of all, the active biofilm formation is a critical key factor which affects the performance of the microbial fuel cell. So it's important to understand active biofilm formation in detail and the electron transfer mechanism and the factor affecting biofilm formation. The most important thing is affecting the biofilm formation is the synergy between the microbe and the electrode surface. As we know, there is three common electron transfer mechanisms. The most important one of them is the direct electron transfer, in which the microbe have electrochemical activity that can degrade, not only degrade the organic substrate, but also can transfer the produced electron to the electrode surface, and that is with the aid of a conductive belly or cytochrome present in their cell. Some microorganisms have no ability to do this action, and so in this case, adding redox mediator to help the electron transfer, and some microbes can secrete self-mediators like secondary metabolites, which can transfer the electron to the electrode surface. On the other side, as we understand the microbe attachment, the anode material is very important on the performance of the microbial fuel cell. Many of the conventional anode material was used in the microbial fuel cell, like carbon-based material, graphite, rod, carbon cloth, and carbon paper. But over years, these conventional materials were replaced with more advanced materials that perform better in the microbial fuel cell. One of the most important advanced anode material is the nanocomposite. This nanocomposite may be metal or oxide-based nanocomposite that affect the ohmic loss and that improve the bacterial cell attachment on the electrode surface. For example, manganese oxide and multi-wood carbon nanocomposite is used for supporting the growth of the electrochemically active consortium of the Enterobacter. Besides the formation of matured biofilm, this composite produce high power density of 370 and potential output reached 710. And this is, as you see, this is characterization, electrochemical characterization of this nanocomposite compared with the pure graphite, and this is the same characterization of the biofilm produced on the surface of the anode. Also, the conductive polymers modified anode can be prepared firstly by the modification of the electrode material for better bacterial cell attachment. Also, for improving the anodic performance, we may doping silver nanomaterial with this conductive polymer. For example, many semiconductive polymer like polyalanine, polydopamine, and polypyrrole increase the capacitive properties and biocompatibility and the surface area of the on the surface active surface area of the Okay, on the cathode side, it's important to post the cathode function toward the oxygen reduction reaction, but unfortunately, platinum, which is the most common catalyst, is very expensive, and so we replaced is we use reduced graphene oxide nanosheet loaded with platinum nanoparticle, and it was demonstrated that the power density produced by this microbial fluid cell was reduced by only 5.8% compared to the pure platinum cathode, and the cost was reduced to the half. And so, reduced graphene oxide nanosheet loaded with platinum nanoparticle is a starting point for finding an alternative, economic, and cost-effective cathode material. Also from the other microbial fluid cell component, the membrane or the proton exchange membrane, there are some problems that facing the proton exchange membrane using in the microbial fluid cell, like biofouling and the cost, and so it's important to prepare anti-fouling composite membrane or changing physical and chemical properties of the existing membrane, or coating the membrane with anti-fouling agents. From the other factors that affecting the microbial fluid cell performance, the pH is a very important parameter that affects the bacterial growth and overall performance of the microbial fluid cell. It's well observed that the optimal pH for the perfect microbial fluid cell performance was restricted to the neutral or near neutral from 6 to 8 range. And also there are several factors such as ion transfer, substrate oxidation or oxygen reduction are pH dependent during the microbial fluid cell operation. Their effect can be controlled by using appropriate catalyst or novel ion exchange membrane, or by adding some buffering agent. Also, temperature affects greatly on the bacterial biofilm, as the temperature affects their growth and electrocatalytic activity. Most of the microbial fluid cell studies have been performed in mesophilic range between 15 and 40 Celsius, which supports that the most electroactive bacteria which used in the microbial fluid cell is mesophilic. Also, the substrate type and concentration have a great effect on the microbial fluid cell performance. As in the microbial fluid cell, we can use different substrate ranging from simple sugar to complex carbohydrates and artificial or real wastewater. Also, it was observed that in high concentration of substrate can have determinant effect on the biofilm due to substrate inhibition. Finally, we can conclude that there are some challenges that need to be addressed to make the microbial fluid cell technology economically viable. Then it's important to understand the electroactive biofilm in detail, the electron transfer mechanism and the factor affecting the biofilm formation. And ideal electrode materials need to present some basic properties that lead to obtaining significant result and improving the microbial fluid cell performance. Finally, high efforts are required to overcome these difficulties and enhance the overall performance of the microbial fluid cell before the industrial scale applications. Finally, thank you.
Finally, the speaker in this session, Engineer Kamel Sisti. He has completed his master's degree at Celestian University of Technology in Poland. He is the PhD student at the Institute of Machinery of Polish Academy Science. He has been ceramic assistant editor in oven chemistry in the Gadallah oven and published 9 papers in reviewed journals. Can you start your presentation? Do you hear me?
Yes, I have presentation. I was thinking that I'm sharing.
You have to start.
Okay. So, good morning, everyone. Thank you for giving a floor or screen. So I have a great pleasure to introduce to my presentation, hydrogen and methane production during direct fermentation of cabbage with small oxygen and the addition of small oxygen under low pH conditions. We can observe that the dark fermentation is a kind of process, microbial process, that is finishing from on acidogenesis, and it started from polycarbohydrate waste like sugar, like to transfer by microbes, which if microbes are catch enough stress or not, the process stop on hydrogen production. If not, then we have methane and we have anaerobic digestion. We start here. We have my my properties of materials that I used. So here we see that the bacteria sound inoculous properties of total solid. So not without water of 1%, and volatile is only organic matter is 29 to 29%. In pH 8, we use 2 sour cabbage with high volatile solids, which is the fresh sour cabbage in fresh style, and the second, it is the low after longer time of pickling, because sour cabbage is the kind of cabbage that we put in a fermentation of lactic acid, and we take two kinds. First is fresh sour cabbage, and then is pickle longer. So here we have the setup, my microbial setup, and as we see, these are reactors, 2 liters. Here we have oxygen dosing, and here we have collecting the hydrogen. And as we see next, we have results of hydrogen production of different oxygen flow rate. You see that in case of high volatile solid, so fresh sour cabbage, the hydrogen yield is usually higher, much higher than in case of pickling or better fermented sour cabbage, unless of oxygen flow rate to 1. So we adding this oxygen twice per day, and we observe that in different oxygen flow rate we have different hydrogen yield, and in case of 0.8 we have the highest hydrogen yield. And here we have the common production as common hydrogen production, and we observe that this hydrogen is the highest for 0.8, is the cumulative, so overall hydrogen production. We also checked for basic, but the basic pretreatment of pH 9 doesn't give interesting results. Yes, and here we have the same result of methane production during this oxygen flow rate difference. So we see that it is reverse situation, that for methane production is better better pickle material. In case of oxygen flow rate from 0 to 1.6, and we have see that how it's look like in cumulative overall methane production, not by yield. So we see the similar case, and as see how it's look like these results of methane and hydrogen in different oxygen flow rates. So we see the cooperative cumulative hydrogen and cumulative methane on different oxygen flow rates. And we observe that also in case of oxygen flow rate, we have small volumes of ethylene. So it's something new because we can, by this process, obtain also, besides hydrogen and methane, some ethylene, which is promising material for for organics, for polymer chemistry, and conclusion is that hydrogen, in case of small oxygen flow rate of 0.58 milliliters per hour or centimeters, cubic centimeters, increase 3 times hydrogen production. Here are its references and we are finishing this time, and thank you for my presentation.
Thank you. Thank you for your interesting presentation, and this is the end of this session. We will begin session, the final session number 6. Thank you.